So hello everyone, we are here to present rethinking semantic segmentation from a sequence to sequence perspective with the transformer from CVPR 2021. So first, let's start with the introduction. So in general, segmentation in general, generating pixel-wise segmentation, giving the class of the object visible at each pixel or background otherwise. In very beginning, I want to mention that there is something. So this paper get 444 citations in 1 year, which is pretty good. And there's not a lot of novelty in this paper. SATR is more like a move forward of a segmentation experiment of VIT. It brings us a new state of art on the numbers of benchmark and perform a challenge to a top AD20K dataset. As a motivation, authors state that most of the semantic segmentation method are adopt for the convolutional network, as known as FCN. So the goal for author is aim to provide a alternative perspective for semantic segmentations, which are sequence to sequence prediction and is pure transformer encoder. I mean, VIT in here, which can perform tasks without convolution and resolution reduction compared to FCN. Some work relates about segmentation model is FCN, which is the most updated adopted model for segmentation, and another is a transformer. They mentioned Datasets, the STTR and the STR, which Datasets, as we know, that is using instant segmentation, and the STTR and the LSTR is adopt transformer for disparity of estimation and line shape prediction respectively. And besides that, the author also specially mentioned EXO. They say that it is the most related work, which is also leveraged on attention for image segmentation. So here is a key difference between them. First, though that both of them remove the convolutional completely, but EXO still follow the convolutional FCN design in that spatial resolution of feature map is reduced progressively. And secondly, EXO adopt a specially designed EXO attentions, which is less scalable to the standard computing facilities. In contrast, SATR is sequence to sequence prediction model, keep the same spatial resolution throughout, and thus represent a step change in model design. And to maximize the scalability on modern hardware accelerators and facility easy to use, they are stick to the standard self-attention design. And it's worth to mention that SATR is also superior in segmentation accuracy. And in order to better compare to SATR, and as FCN may be new to someone, I'm going to very briefly revise the FCN segmentation and the main difference between CNN. And as you can notice that from the feature that FCN using the whole image instead of patches. So there is three main key expanded to talk about FCN. First is convolutional. So FCN replace a fully connected layer with the correspond to the convolutional layer. So after so let's see here. So in the last three layers, CNN is 3 of the 1 times 1 corner, which is a bunch of the possibility of the output. And in FCN is still convolutional layer. So after many time of convolutional pooling, the image is getting smaller. When it came with when it came to the end, it will become the height and width divided by 32, and that's the smallest dimension for the image in the process, which will produce a heat map, and then it will use upsampling. It will use upsampling to see. We use upsampling to recover the position of the feature of the image and make the image back to the original size. So there will produce like 1,000 of heat map will be upsampling and become the original size, and take all of the pixel among them, and they will take all pixel among them in those heat map and perform a compare and find the volumes with the highest possibility. So it's a pixel-wise prediction and produce a segmentation image. Up to this point, it's already have the segmentation result, but it's not very precise. So they will add a skip layer, which is connect the output of the convolutional layer to the deconvolutional layers and to increase its precision. So next I will transfer to Josh to talk more about the method and what's the strength and weakness about FCN compared to the SATRs.
All right, so let's get started going over the encoder, which for SATR is a standard transformer encoder, as we've seen with VIT and others. And the authors mentioned they use a 16 by 16 patch size across all of their ablations. But the key difference with this model is specifically with the encoder, since the encoder is just a standard transformer, which we can see here is again, the same thing that we've seen before, linear projection to transformer layers, and then off to the decoder to get the final segmented output. They do experiment with a number of encoder variants, however. They use T-base, which is 12 transformer layers, T-large, which is 24 layers, a hybrid baseline, which uses a ResNet 50 FCN encoder, which is then, those outputs are then fed to one of the SATR decoders. And they also make use of pre-trained weights using VIT or DITE pre-trained on ImageNet 1K or 21K. The different encoders, they first started with naive upsampling, which is a 2-layer upsampling method using a 1x1 convolution to a batch norm using ReLU, followed by another 1x1 convolution, which they then bilinearly upsample to the original image size. They then go on to describe progressive upsampling, which instead of using upsampling at the end and going all the way back up to the original input size, they alternate 2 times upsampling with convolutional layers. And they do this operation 4 times to get back to the original input image size. And we can see here the original, the transformer encoder is output to a reshape, which is then convolved, upsampled, until we get to the original input image size. And what you may notice is that this looks quite similar to UNet, which is the architecture here on the bottom, where the decoder is very much based off of the UNet architecture, where we slowly deconvolve and upsample back to the original input size. The key difference being that instead of using a convolutional encoder to get down to a latent vector, we instead use a transformer encoder to get our feature outputs. The authors then describe multi-level feature aggregation, which is conceptually similar to a multi-level pyramid we've seen many times in computer vision. Every layer of the transformer outputs the same size of outputs, however, so that's where the difference is. Instead of with convolution where the output size is reduced by each layer, we have the exact same output for each layer with a transformer. The way they do this operation is they take the outputs from each layer of the transformer, reshape the output for convolution, and then they do an element-wise addition across the layers, pass it off to a 3-layer convolution, and then upscale 4 times, fuse the features along the channel dimension, and then convolve and upscale again. So let's take a look at what this looks like visually. We can see here the outputs from each individual layer of the transformer from layers 6, 12, 18, and 24, which are reshaped and convolved to get these feature maps. And then we do element-wise addition across each of these layers by adding these 2 layers together here, or rather all these layers together here, these 3 here, these 2 here, and then that one alone goes off and then is convolved with that 3-layer convolution and upscaled. They're fused along the channel dimension, convolved, and then upscaled again to get the original input image size. So I'll now pass it off to Brandon to cover the loss function.
Okay, can everyone see?
Hey, Brendan, what's a noise in your background? Is there some noise?
Is there some background noise? Let me.
Okay, continue.
Okay. So for the loss function for all of their experiments, they're using a pixel-wise cross-entropy loss, but the authors also implement an auxiliary loss. And what this does is it uses outputs from the different encoder layers to calculate a loss. And this kind of helps get the loss to the earlier layers in this deep model where we have 24 transformer layers. So the layers that they use for each model, for the naive, they use 10, 15, and 20. For the pop sampling method, they do 10, 15, 20, and 24. And then for MLA, they do 6, 12, 18, and 24. The outputs that they get are sent through a 2-layer feed-forward network before they are sent to bilinear interpolation so that we can get it back to the original image size. So our overall loss function will look like this. We have our pixel-wise cross-entropy loss from the very end of our network after the decoder, and then we add on all of the auxiliary losses. So to kind of show what the auxiliary loss will look like in our model, we have an image and an encoder. For simplicity, I'm only going to show 4 layers for the transformer encoder. And our normal pipeline is going to look like this, where we take the image, send it through all of our transformer encoder layers into whatever upsampling method we want to use, and then send that to our pixel-wise cross-entropy loss. When we add on the auxiliary loss, we use this special auxiliary head that has the feed-forward and bilinear interpolation. And then we take the output from this layer. As an example, I'm just using layer 2. We feed that into our auxiliary head. And then once we bilinearly interpolate up to the original image size, we get a pixel-wise cross-entropy loss that they label as the auxiliary loss. This isn't new to this paper. Auxiliary losses have been around for a while. This is just something that they use to kind of help the model train. And so to show what the full model looks like with all of its losses, I'll use SATR pup as an example. So again, we take an image and we feed it into our transformer encoder. I'm going to be using the 24-layer encoder as the example. And then we'll take different layers, layer 10, 15, and 20, and send them to auxiliary heads. And then because SATR pup uses the 24th layer for an auxiliary head, that is sent down here and also up to the progressive upsampling method. And then everything is sent to its own pixel-wise cross-entropy loss. So this is kind of our overall model pipeline. Now, some of the data sets that they use in their experiments, they use Cityscapes, which has 19 object classes with 3,000 training, 500 validation, and 1,500 testing. Specifically, Cityscapes has a lot of high-resolution images, so this is 2048 by 1024. They also test on ADE20K, which has 150 semantic classes with 20,000 training images, 2,000 validation, and 3,000 testing. and they test on Pascal context, which has 60 classes with 5,000 training images and 5,000 validation images. And so here I have some examples. This first one's from Cityscapes, then ADE20K, and Pascal context. The authors specifically focus on ADE20K and those results because when they were submitting this paper, they actually used this as part of a challenge on the ADE20K dataset. Some of the details about the experiments. For augmentations, they do a random resize where the ratio is between 0.5 and 2. They do random cropping, which is specific to the dataset size, and they do a random horizontal flip. For batch sizes, they use 16 for ADE20K and the Pascal context, and for Cityscapes, they use a batch size of 8. They implement a polynomial learning rate schedule and a stochastic gradient descent optimizer with a momentum of 0.9. The initial learning rate is 0.001 for ADE20K and Pascal, and then 0.01 for Cityscapes. And interestingly, instead of training for a specific number of epochs, the authors use the number of iterations of the data loader to define when they stop the training. So they typically use 80,000 iterations or 160,000 iterations. Now, when they're testing this data set, they do two different kinds of testing, single scale and multi-scale. What single scale testing is they just have a set scaling value for the image. So they'll take the image, get a crop of it, scale that crop to whatever our set scaling value is, and then they do a random horizontal flip. For the multi-scaling, there are many different scale values that can be used on an image. So for this, they crop the image and then they pick a scale either from a range or just a preset list of scales, and then they do the horizontal flip. Both of these testing methods will utilize a sliding window to make sure that they use all of the testing or validation image when they're doing this testing. And all the auxiliary heads are ignored whenever they're doing testing as well. So now I'll pass it on to Alejandro to do the state-of-the-art comparison.
Can anyone see my screen?
Yes.
Yeah, cool. All right, so for the comparison to state-of-the-art, they did results on the Cityscapes validation. Here they achieved a new IOU score. And so this was the original SOTA holder, and then their score was higher. And now for the Cityscapes test, they were actually behind of the state-of-the-art model, and they're behind the CCNet. So CCNet triumphed over the Axel Deep Lab and the SATR. And we're saying this because the results use fine and coarse annotated data. For the results on the Cityscapes, on the left-hand side, as the qualitative results, you can see that the car has like these segmentation issues on the bottom. It's not segmentating correctly, and the right side SATR segmentates that better. So this is another example, and on the top of the couple, you can see the segmentation result not doing correctly compared to the SATR on the right-hand side. And then for the last example, there is the same kind of situation on the left-hand side of that wall. It's not segmenting properly against the SATR. On the AD20K results, they achieved the new state-of-the-art score for above every other model. And this is every variant of SATR achieve a better score. So the SATR MLAs achieved the highest score at 50, and that transfers over to the Deep Lab implementation. We see that it works with different decoders and not just the MLA, and it outperforms, and the MLA outperforms the PUP. Multi-scale performance also is better than single scale, so that's shown with the SS and MS. For qualitative results on the 8020K, on the left-hand side, you can see that's not segmenting properly the photo, that little blotch. On the right-hand side, SATR segmentates it much better. So, and the second example, same kind of ordeal. The bleachers are not being segmented properly, and on the right-hand side, they are. Another comparison of the Pascal context, it is a huge improvement on the baseline. And so this is the original SOTA, and then SATR perform much better. So it's a new IOU score holder. On the quality results in the Pascal context, you see that on the bottom of the runway, the left-hand side is not segmented properly. On the right-hand side, it is. Same thing with the surfboard. It's all sort of a mess on the left-hand side. On the right-hand side, it's much better segmented. And then here's a comparison of the SATR trained on a Pascal context with the attention maps visualized. And so the airplane, very well segmented, the dog, the tram, the goat. You would see similar performance, but with the little boy, I think that is not very well segmented, and the cows are kind of hit or miss. So. As for result on the features, if you see the input, the more Z layers, the better the segmentation results get. So as an example, I'll show you layers at layer 1, layer 9, you see improvement, it's better segmented, especially between layer 9 and 17, there's a huge contrast, and then as well as layer 24. And so for this table, it's analysis between the SATR variants. And so there's all the different variants they implemented, and the PUP scores better than all the other SATR variants, excluding the hybrids and the FCN. The SATR is better than those. And so the PUP outperforms all the other variants on the cityscapes. So that's better than the MLA implementation and the FPN. And then the SATR base performs the hybrid base in this scenario as well, but only when it has more of the training schedule at 80K instead of 40K. And then the PUP trained with a backbone of the DEIT is better performing than a randomly pre-trained model. And so that's evident with these two examples. And then on the 80-20 benchmark, the SATR MLA performs slightly better than SATR PUP, but much more superior than SATR native and variant. So this is also a good example of multi-scale versus single scale performance difference. So multi-scale will perform better than single scale. For the SATR variants FCN comparison, both in the cityscapes and the 80-20K, here are all the SATR variants, and then they perform better than the FCN models. And so and every variant of SATR performs better. And then it's also a really good example of how pre-training takes a big role in the performance. So in the conclusion, alternative method for semantic segmentation is sequence-to-sequence prediction network over the FCN. It eliminates the reliance on the FCN. It is shown that transformers can model global contexts at every stage of the feature learning, and it achieves state-of-the-art of 80E20K and a Pascal context, as well as competitive results on the cityscapes and the services.